Welcome back. Let's read this one.
Bipolar junction transistor. BJT and junction transistor redirect here. For other uses, see BJT, disambiguation, and junction transistor, disambiguation. A bipolar junction transistor, BJT, is a type of transistor that uses both electrons and electron holes as charge carriers. In contrast, a unipolar transistor, such as a field effect transistor, FET, uses only one kind of charge carrier. A bipolar transistor allows a small current injected at one of its terminals to control a much larger current flowing between the terminals, making the device capable of amplification or switching. BJTs use two p-n junctions between two semiconductor types, N-type and P-type, which are regions in a single crystal of material. The junctions can be made in several different ways, such as changing the doping of the semiconductor material as it is grown, by depositing metal pellets to form alloy junctions, or by such methods as diffusion of N-type and P-type doping substances into the crystal. The superior predictability and performance of junction transistors quickly displaced the original point contact transistor. Diffused transistors, along with other components, are elements of integrated circuits for analog and digital functions. Hundreds of bipolar junction transistors can be made in one circuit at very low cost. Bipolar transistor integrated circuits were the main active devices of a generation of mainframe and mini-computers, but most computer systems now use complementary metal oxide semiconductor, CMOS, integrated circuits relying on the field effect transistor, FET. Bipolar transistors are still used for amplification of signals, switching, and in mixed-signal integrated circuits using BiCMOS. Specialized types are used for high-voltage switches, for radio frequency, RF, amplifiers, or for switching high currents. Current direction conventions, edit. By convention, the direction of current on diagrams is shown as the direction that a positive charge would move. This is called conventional current. However, current in metal conductors is generally due to the flow of electrons. Because electrons carry a negative charge, they move in the direction opposite to conventional current. On the other hand, inside a bipolar transistor, currents can be composed of both positively charged holes and negatively charged electrons. In this article, current arrows are shown in the conventional direction, but labels for the movement of holes and electrons show their actual direction inside the transistor. Arrow direction, edit. The arrow on the symbol for bipolar transistors indicates the p-n junction between base and emitter and points in the direction in which conventional current travels. Function, edit. This section may be too technical for most readers to understand. Please help improve it to make it understandable to non-experts, without removing the technical details. July 2012. Learn how and when to remove this message. BJTs exist as PNP and NPN types, based on the doping types of the three main terminal regions. An NPN transistor comprises two semiconductor junctions that share a thin p-doped region, and a PNP transistor comprises two semiconductor junctions that share a thin n-doped region. N-type means doped with impurities, such as phosphorus or arsenic, that provide mobile electrons, while P-type means doped with impurities, such as boron, that provide holes that readily accept electrons. NPN BJT with forward-biased BE junction and reverse-biased BC junction. Charge flow in a BJT is due to diffusion of charge carriers, electrons and holes, across a junction between two regions of different charge carrier concentration. The regions of a BJT are called emitter, base, and collector. A discrete transistor has 3 leads for connection to these regions. Typically, the emitter region is heavily doped compared to the other 2 layers, and the collector is doped more lightly, typically 10 times lighter, than the base. By design, most of the BJT collector current is due to the flow of charge carriers injected from a heavily doped emitter into the base where they are minority carriers, electrons in NPNs, holes in PNPs, that diffuse toward the collector, so BJTs are classified as minority carrier devices. In typical operation, the base emitter junction is forward biased, which means that the p-doped side of the junction is at a more positive potential than the n-doped side, and the base collector junction is reverse biased. When forward bias is applied to the base emitter junction, the equilibrium between the thermally generated carriers and the repelling electric field of the emitter depletion region is disturbed. This allows thermally excited carriers, electrons in NPNs, holes in PNPs, to inject from the emitter into the base region. These carriers create a diffusion current through the base from the region of high concentration near the emitter toward the region of low concentration near the collector. To minimize the fraction of carriers that recombine before reaching the collector base junction, the transistor's base region must be thin enough that carriers can diffuse across it in much less time than the semiconductor's minority carrier lifetime. Having a lightly doped base ensures recombination rates are low. In particular, the thickness of the base must be much less than the diffusion length of the carriers. The collector base junction is reverse biased, and so negligible carrier injection occurs from the collector to the base, but carriers that are injected into the base from the emitter, and diffuse to reach the collector base depletion region, are swept into the collector by the electric field in the depletion region. The thin shared base and asymmetric collector-emitter doping are what differentiates a bipolar transistor from 2 separate diodes connected in series. Voltage, current, and charge control, edit. The collector-emitter current can be viewed as being controlled by the base emitter current, current control, or by the base emitter voltage, voltage control. These views are related by the current-voltage relation of the base emitter junction, which is the usual exponential current-voltage curve of a p-n junction diode. The explanation for collector current is the concentration gradient of minority carriers in the base region. Due to low-level injection, in which there are much fewer excess carriers than normal majority carriers, the ambipolar transport rates, in which the excess majority and minority carriers flow at the same rate, is in effect determined by the excess minority carriers. Detailed transistor models of transistor action, such as the Gummel-Poon model, account for the distribution of this charge explicitly to explain transistor behavior more exactly. The charge control view easily handles phototransistors, where minority carriers in the base region are created by the absorption of photons, and handles the dynamics of turn-off, or recovery time, which depends on charge in the base region recombining. However, because base charge is not a signal that is visible at the terminals, the current and voltage control views are generally used in circuit design and analysis. In analog circuit design, the current control view is sometimes used because it is approximately linear. That is, the collector current is approximately beta sub cap F times the base current. Some basic circuits can be designed by assuming that the base emitter voltage is approximately constant and that collector current is beta times the base current. However, to accurately and reliably design production BJT circuits, the voltage control model, for example the Ibis-Moll model, is required. The voltage control model requires an exponential function to be taken into account, but when it is linearized such that the transistor can be modeled as a transconductance, as in the Ibis-Moll model, design for circuits such as differential amplifiers again becomes a mostly linear problem, so the voltage control view is often preferred. For translinear circuits, in which the exponential IV curve is key to the operation, the transistors are usually modeled as voltage-controlled current sources whose transconductance is proportional to their collector current. In general, transistor-level circuit analysis is performed using SPICE or a comparable analog circuit simulator, so mathematical model complexity is usually not of much concern to the designer, but a simplified view of the characteristics allows designs to be created following a logical process. Turn on, turn off, and storage delay, edit. Main article, Baker clamp. Bipolar transistors, and particularly power transistors, have long base storage times when they are driven into saturation. The base storage limits turn-off time in switching applications. A Baker clamp can prevent the transistor from heavily saturating, which reduces the amount of charge stored in the base and thus improves switching time. Transistor characteristics, alpha, alpha, and beta, beta, edit. The proportion of carriers able to cross the base and reach the collector is a measure of the BJT efficiency. The heavy doping of the emitter region and light doping of the base region causes many more electrons to be injected from the emitter into the base than holes to be injected from the base into the emitter. A thin and lightly doped base region means that most of the minority carriers that are injected into the base will diffuse to the collector and not recombine. Common emitter current gain, edit. The common emitter current gain is represented by F or the H parameter HFE. It is approximately the ratio of the collector's direct current to the base's direct current in forward active region. The F subscript is used to indicate the forward active mode of operation. It is typically greater than 50 for small signal transistors, but can be smaller in transistors designed for high power applications. Both injection efficiency and recombination in the base reduce the BJT gain. Common base current gain, edit. Another useful characteristic is the common base current gain, F. The common base current gain is approximately the gain of current from emitter to collector in the forward active region. This ratio usually has a value close to unity, between 0.980 and 0.998. It is less than unity due to recombination of charge carriers as they cross the base region. Alpha and beta are related by the following identities. Two lines. Line 1, alpha subcap F equals the fraction with numerator I subcap C and denominator I subcap E, beta subcap F equals the fraction with numerator I subcap C and denominator I subcap B, line 2, alpha subcap F equals the fraction with numerator beta subcap F and denominator 1 plus beta subcap F, long left right double arrow, beta subcap F equals the fraction with numerator alpha subcap F and denominator 1 minus alpha subcap F period. Beta is a convenient figure of merit to describe the performance of a bipolar transistor, but is not a fundamental physical property of the device. Bipolar transistors can be considered voltage-controlled devices. Fundamentally, the collector current is controlled by the base emitter voltage. The base current could be considered a defect and is controlled by the characteristics of the base emitter junction and recombination in the base. In many designs, beta is assumed high enough so that base current has a negligible effect on the circuit. In some circuits, generally switching circuits, sufficient base current is supplied so that even the lowest beta value a particular device may have will still allow the required collector current to flow. Structure, edit. Simplified cross-section of a planar NPN bipolar junction transistor. BJTs consists of three differently doped semiconductor regions: the emitter region, the base region and the collector region. These regions are, respectively, P-type, N-type and P-type in a PNP transistor, and N-type, P-type and N-type in an NPN transistor. Each semiconductor region is connected to a terminal, appropriately labeled emitter, E, base, B, and collector, C. The base is physically located between the emitter and the collector and is made from lightly doped, high-resistivity material. The collector surrounds the emitter region, making it almost impossible for the electrons injected into the base region to escape without being collected, thus making the resulting value of alpha very close to unity, and so, giving the transistor a large beta. A cross-section view of a BJT indicates that the collector-base junction has a much larger area than the emitter-base junction. The bipolar junction transistor, unlike other transistors, is usually not a symmetrical device. This means that interchanging the collector and the emitter makes the transistor leave the forward active mode and start to operate in reverse mode. Because the transistor's internal structure is usually optimized for forward mode operation, interchanging the collector and the emitter makes the values of alpha and beta in reverse operation much smaller than those in forward operation. Often the alpha of the reverse mode is lower than 0.5. The lack of symmetry is primarily due to the doping ratios of the emitter and the collector. The emitter is heavily doped, while the collector is lightly doped, allowing a large reverse bias voltage to be applied before the collector-base junction breaks down. The collector-base junction is reverse biased in normal operation. The reason the emitter is heavily doped is to increase the emitter injection efficiency, the ratio of carriers injected by the emitter to those injected by the base. For high current gain, most of the carriers injected into the emitter-base junction must come from the emitter. The low-performance lateral bipolar transistors sometimes used in CMOS processes are sometimes designed symmetrically, that is, with no difference between forward and backward operation. Small changes in the voltage applied across the base emitter terminals cause the current between the emitter and the collector to change significantly. This effect can be used to amplify the input voltage or current. BJTs can be thought of as voltage-controlled current sources, but are more simply characterized as current-controlled current sources, or current amplifiers, due to the low impedance at the base. Early transistors were made from germanium, but most modern BJTs are made from silicon. A significant minority are also now made from gallium arsenide, especially for very high-speed applications, see HBT, below. The heterojunction bipolar transistor, HBT, is an improvement of the BJT that can handle signals of very high frequencies up to several hundred GHz. It is common in modern ultrafast circuits, mostly RF systems. Two commonly used HBTs are silicon germanium and aluminum gallium arsenide, though a wide variety of semiconductors may be used for the HBT structure. HBT structures are usually grown by epitaxy techniques like MOCT and MBE. Regions of operation, edit. Bipolar transistors have four distinct regions of operation, defined by BJT junction biases. Forward active, or simply active. The base emitter junction is forward biased and the base collector junction is reverse biased. Most bipolar transistors are designed to afford the greatest common emitter current gain, F, in forward active mode. If this is the case, the collector emitter current is approximately proportional to the base current, but many times larger, for small base current variations. Reverse active, or inverse active or inverted. By reversing the biasing conditions of the forward active region, a bipolar transistor goes into reverse active mode. In this mode, the emitter and collector regions switch roles. Because most BJTs are designed to maximize current gain in forward active mode, the F in inverted mode is several times smaller, 2-3 times for the ordinary germanium transistor. This transistor mode is seldom used, usually being considered only for fail-safe conditions and some types of bipolar logic. The reverse bias breakdown voltage to the base may be an order of magnitude lower in this region. Saturation. With both junctions forward biased, a BJT is in saturation mode and facilitates high current conduction from the emitter to the collector, or the other direction in the case of NPN, with negatively charged carriers flowing from emitter to collector. This mode corresponds to a logical on, or a closed switch. Cutoff. In cutoff, biasing conditions opposite of saturation, both junctions reverse biased, are present. There is very little current, which corresponds to a logical off, or an open switch. Although these regions are well defined for sufficiently large applied voltage, they overlap somewhat for small, less than a few hundred millivolts, biases. For example, in the typical grounded emitter configuration of an NPN BJT used as a pull-down switch in digital logic, the off state never involves a reverse biased junction because the base voltage never goes below ground. Nevertheless, the forward bias is close enough to zero that essentially no current flows, so this end of the forward active region can be regarded as the Q-TAF region. Active mode transistors in circuits, edit. The diagram shows a schematic representation of an NPN transistor connected to two voltage sources. The same description applies to a PNP transistor with reversed directions of current flow and applied voltage. This applied voltage causes the lower PN junction to become forward biased, allowing a flow of electrons from the emitter into the base. In active mode, the electric field existing between base and collector, caused by VCE, will cause the majority of these electrons to cross the upper PN junction into the collector to form the collector current IC. The remainder of the electrons recombine with holes, the majority carriers in the base, making a current through the base connection to form the base current, IB. As shown in the diagram, the emitter current, IE, is the total transistor current, which is the sum of the other terminal currents, i.e. IE equals IB plus IC. In the diagram, the arrows representing current point in the direction of conventional current. The flow of electrons is in the opposite direction of the arrows because electrons carry negative electric charge. In active mode, the ratio of the collector current to the base current is called the DC current gain. This gain is usually 100 or more, but robust circuit designs do not depend on the exact value, for example see op-amp. The value of this gain for DC signals is referred to as H sub FE, and the value of this gain for small signals is referred to as H sub FE. That is, when a small change in the currents occurs, and sufficient time has passed for the new condition to reach a steady state. H sub FE is the ratio of the change in collector current to the change in base current. The symbol beta is used for both H sub FE and H sub FE. The emitter current is related to V sub B exponentially. At room temperature, an increase in V sub B by approximately 60 MV increases the emitter current by a factor of 10. Because the base current is approximately proportional to the collector and emitter currents, they vary in the same way. History, edit. The bipolar point contact transistor was invented in December 1947 at the Bell Telephone Laboratories by John Bardeen and Walter Brattain under the direction of William Shockley. The junction version known as the bipolar junction transistor, BJT, invented by Shockley in 1948, was for 3 decades the device of choice in the design of discrete and integrated circuits. Nowadays, the use of the BJT has declined in favor of CMOS technology in the design of digital integrated circuits. The incidental low-performance BJTs inherent in CMOS ICs, however, are often utilized as bang-up voltage reference, silicon band-gap temperature sensor and to handle electrostatic discharge. Germanium transistors, edit. The germanium transistor was more common in the 1950s and 1960s but has a greater tendency to exhibit thermal runaway. Since germanium p-n junctions have a lower forward bias than silicon, germanium transistors turn on at lower voltage. Early manufacturing techniques, edit. Various methods of manufacturing bipolar transistors were developed. One-point contact transistor, first transistor ever constructed, December 1947, a bipolar transistor, limited commercial use due to high cost and noise. One tetrode point contact transistor having two emitters. It became obsolete in the middle 1950s. Two junction transistors. One grown junction transistor, first bipolar junction transistor made. Invented by William Shockley at Bell Labs on the 23rd of June, 1948. Patent filed on the 26th of June, 1948. Two alloy junction transistor emitter and collector alloy beads fused to base. Developed at General Electric and RCA in 1951. One microalloy transistor, MAT, high-speed type of alloy junction transistor. Developed at Philco. Two microalloy diffused transistor, MAT, high-speed type of alloy junction transistor, speedier than MAT, a diffused base transistor. Developed at Philco. Three post-alloy diffused transistor, PAT, high-speed type of alloy junction transistor, speedier than MAT, a diffused base transistor. Developed at Philips. Three tetrode transistor, high-speed variant of grown junction transistor or alloy junction transistor with two connections to base. Four surface barrier transistor, high-speed metal barrier junction transistor. Developed at Philco in 1953. 5 drift field transistor, high-speed bipolar junction transistor. Invented by Herbert Kroemer at the Central Bureau of Telecommunications Technology of the German Postal Service, in 1953. 6 spacestor around 1957. 7 diffusion transistor, modern type bipolar junction transistor. Prototypes developed at Bell Labs in 1954. 1 diffused base transistor, first implementation of diffusion transistor. 2 Mesa transistor developed at Texas Instruments in 1957. 3 planar transistor, the bipolar junction transistor that made mass-produced monolithic integrated circuits possible. Developed by Jean Huerny at Fairfield in 1959. 8 epitaxial transistor, a bipolar junction transistor made using vapor phase deposition. See epitaxy. Allows very precise control of doping levels and gradients. Theory and modeling, edit. BJTs can be thought of as two diodes, p-n junctions, sharing a common region that minority carriers can move through. A PNP BJT will function like two diodes that share an N-type cathode region, and the NPN like two diodes sharing a P-type anode region. Connecting two diodes with wires will not make a BJT, since minority carriers will not be able to get from one PN junction to the other through the wire. Both types of BJT function by letting a small current input to the base control an amplified output from the collector. The result is that the BJT makes a good switch that is controlled by its base input. The BJT also makes a good amplifier, since it can multiply a weak input signal to about 100 times its original strength. Networks of BJTs are used to make powerful amplifiers with many different applications. In the discussion below, focus is on the NPN BJT. In what is called active mode, the base emitter voltage, V sub B, and collector base voltage, V sub CB, are positive, forward biasing the emitter base junction and reverse biasing the collector base junction. In this mode, electrons are injected from the forward biased N-type emitter region into the P-type base where they diffuse as minority carriers to the reverse biased N-type collector and are swept away by the electric field in the reverse biased collector base junction. For an illustration of forward and reverse bias, see semiconductor diodes. Large signal models, edit. In 1954, Joel James Ivers and John L. Moll introduced their